Temper embrittlement. Temper embrittlement is a reduction of toughness due to the metallurgical change that can occur in some low alloy steels as a result of long-term exposure in the temperature range of about 650F to 1070F, 343C to 577C. This change causes an upward shift in the ductile to brittle transition temperature as measured by Sharpie impact testing. Although the loss of toughness is not evident at operating temperatures, equipment that is temper embrittled may be susceptible to brittle fracture during startup and shutdown. Affected materials: primarily 2.25 1 moly, chrome 1 moly, low alloy steel, 3 chrome 1 moly to a lesser extent, and the high strength low alloy chrome moly, vanadium, rotor steels. Older generation 2.25 chrome 1 moly materials manufactured prior to 1972 may be particularly susceptible. Some high-strength low alloy steels are also susceptible. The chrome half moly, 1 chrome half moly, carbon half moly, 1 chrome half moly, and 1.25 chrome half moly alloy steels are not significantly affected by temper embrittlement. However, other high temperature damage mechanisms promote metallurgical changes that can alter the toughness of high temperature ductility of these materials. Refer to API 934C and 934D for additional information. Weld materials are generally more affected than today's low impurity base metals. Critical factors: alloy steel composition, thermal history, metal temperature, and exposure time are critical factors. Susceptibility to temper embrittlement is largely determined by the presence of alloying elements, manganese and silicon, and the tramp elements, phosphorus, tin, antimonium, and arsenic. The strength levels and heat treatment fabrication history should also be considered. Temper embrittlement of 2.25 chrome 1 moly steels develop more quickly at 900F than in the 800 to 850F range, but the damage is more severe after long-term exposure at 850F. Some embrittlement can occur during fabrication heat treatments, but most of the damage occurs over many years of service in the embrittlement temperature range. This form of damage will significantly reduce the structural integrity of a component containing a crack-like flaw. An evaluation of the material's toughness may be required depending on the flaw type, the severity of the environment, and the operating conditions, particularly in hydrogen service. Affected units or equipment. Temper embrittlement occurs in a variety of process units after long-term exposure to temperatures above 650F. It should be noted that there have been very few industry failures related directly to temper embrittlement. Equipment susceptible to temper embrittlement is often found in hydroprocessing units, particularly reactors, hot feed effluent exchanger components, and hot HP separators. Other units with the potential for temper embrittlement include Cadillac reforming units, reactors and exchangers, FCC reactors, coker, and vessel braking units. Welds in these alloys are often more susceptible than base metal and should be evaluated. Morphology of damage and appearance. Temper embrittlement is a metallurgical change that is not readily apparent and can be confirmed through impact testing. Damage due to temper embrittlement result in catastrophic brittle fracture. Temper embrittlement can be identified by the upward shift in the ductile to brittle transition temperature measured by the Sharpie V-notch impact test as compared to the non-embrittled or de-embrittled materials. See Figure 4-5. Another important characteristic of temper embrittlement is that there is no effect on the upper shelf energy. SEM fractiographs are severely tempered embrittlement materials show primarily intergranular cracking due to impurity segregation at grain boundaries. Prevention and mitigation. Existing materials. Temper embrittlement cannot be prevented if the materials contains critical levels of the embrittling impurities, elements, and is exposed to the embrittling temperature range. To minimize the possibility of brittle fracture during startup and shutdown, many refiners use a pressurized sequence to eliminate system pressure to about 25% of maximum design pressure for temperatures below a minimum pressurization temperature. Note that the MPT is not a single point, but rather a pressure temperature envelope which defines safe operating conditions to minimize the likelihood of brittle fracture. MPTs generally range from 300 F for the earliest, most highly tempered and brittle steels down to 125 F for newer temper embrittlement resistant steels, as required to also minimize effects of hydrogen embrittlement. If weld repairs are required, the effects of temper embrittlement can temporarily be reversed, de-embrittled by heating at 1150 F for 2 hours per inch of thickness and rapidly cooling to room temperature. It is important to note that re-embrittlement will occur over time if the material is re-exposed to the embrittling temperature range. New materials. The best way to minimize the likelihood and extent of temper embrittlement is to eliminate the acceptance levels of manganese, silicone, phosphorus, tin, antimony, arsenic in the base metal and welding consumables. In addition, strength levels and post-weld heat treatment procedures should be specified and carefully controlled. A common way to minimize temper embrittlement is to limit the J factor for base metal and the X factor for weld metal, based on the material composition as follows. Your J equals silicone plus manganese times phosphorus plus tin, I believe, times 10 to the 4th power elements in weight percentages. Elements in parts per million would be your X factor. 10P plus 5SB plus 4SN plus AS divided by 100. Typical J and X factors used for 2.25 chrome steels are a maximum of 100 and 15 respectively. Studies have shown that limiting the P plus SN to less than 0.01% is sufficient to minimize temper embrittlement because SN plus MN control the rate of embrittlement. Or silicone and manganese. A newer and less widely used factor called the equivalent phosphorus content has been developed for base metals and weld metals and is defined as follows, given by phosphorus equivalent equals carbon plus manganese plus the product of moly chrome divided by 3 plus silicone divided by 4 plus 3.5 times bracket parentheses 10 times phosphorus plus parentheses 5 times 10 plus or SB plus parentheses 4 times SN parentheses plus AS parentheses elements and weight. So expert metallurgical advice should be solicited to determine acceptable compositions, toughness, and strength levels, as well as appropriate welding, fabrication, and heat treatment procedures for new alloy, low alloy, heavy wall equipment, and low alloy equipment operating in the temper embrittlement or creep range. Inspection and monitoring. A common method of monitoring is to store blocks of original heats of the alloy steel material inside the reactor. Samples are periodically removed from these blocks for impact testing to monitor establish the ductile brittle transition temperature. The test block should be strategically located near the top and bottom of the reactor to make sure that the test material is exposed to both inlet and outlet conditions. Process conditions should be monitored to ensure that a proper pressurization sequence is followed to help prevent brittle fracture due to temper embrittlement. Plot of C, V, and toughness as a function of temperature, showing a shift in the 40 foot-pound transition temperature. Temperature on this top axis, C, V, and impact energy in foot-pounds on this axis. Welded plus post-weld heat treatment. Welded plus post-weld heat treatment plus step age. and then CVN impact energy on this axis. 424, strain aging. Strain aging is a form of damage mostly found in older vintage carbon steels and chrome half-moly steels, low alloy steels, under the combined effects of deformation and aging at an intermittent temperature. The results in an increase in hardness and strength with reduction in ductility and toughness. Affected materials, mostly older pre-1980 carbon steels with a large grain size and carbon half-moly low alloy steels. Critical factors. Steel composition and manufacturing process determines steel susceptibility. Steel manufactured by the Bessemer or open hearth process contain higher levels of critical impurity elements than newer steel manufactured by the basic oxygen furnace process. In general, steels made by BOF and fully killed with aluminum are not susceptible. This effect is found in rimmed and capped steels with higher levels of nitrogen and carbon, but not in the modern fully killed carbon steels manufactured to a fine grain practice. Strain aging effects are observed in materials that have been cold worked and placed into service at intermittent temperatures without stress relieving. Strain aging is a major concern for equipment that contains cracks. If susceptible materials are plastically deformed and exposed to intermittent temperatures, the zones of deformed materials may become hardened and less ductile. The phenomenon has been associated with several vessels that have failed by brittle fracture. The pressurization sequence versus temperature is a critical issue to brittle fracture of susceptible materials. Strain aging can also occur when welding in the vicinity of cracks and notches in a susceptible material. Strain aging is most likely to occur in thick wall vessels manufactured from susceptible materials that have not been stress relieved. Appearance and morphology of damage. Strain aging can result in the formation of brittle cracks that are revealed through detailed metallurgical analysis, but damage most likely will not be identified as strain aging until fracture has already occurred. Prevention and mitigation. Strain aging is not an issue for newer steels that contain low levels of interstitial impurity elements and sufficient aluminum, 0.015% by weight or greater, to fully deoxidize the steel. For older equipment, extra care should be taken to avoid the potentially damaging effects of strain aging by avoiding stressing or pressurizing equipment until the temperature reaches an acceptable level where the risk of brittle fracture is low. Refer to the A in the UCS 66 of the AMSC Code Section 8, Division 1 for pressurization temperatures of vessels susceptible to strain aging effects. Applying post-weld heat treatment to weld repairs of susceptible material will eliminate the effects of strain aging. Where post-weld heat treatment is not possible, buttering should be considered to minimize welding of an old material under restraint. Inspection and monitoring. Inspection and monitoring are not used to control strain aging. Related mechanisms. When deforming occurs at the intermittent temperature, the mechanism referred to as dynamic strain aging. Blue brittleness is another form of strain aging. .885 embrittlement. Description: damage. .885 embrittlement is a loss of toughness due to the metallurgical changes that occur in alloys containing a ferrite phase as a result of exposure to temperatures in the range of 600 to 1000 F. 400 series SS, 405, 409, 410, 410S, 430, and 446 are affected materials. Duplex stainless steel such as alloys 2205, 2304, and 20507 are also affected. Critical factors. The alloy composition, particularly chromium content, amount of ferrite phase, and operating temperatures are critical factors. Increasing amounts of ferrite phase increases susceptibility to damage when operating in a high temperature range of concern. A dramatic increase in the ductile to brittle transition temperature will occur. A primary consideration in operating in the temperature within the critical temperature range. Damage is cumulative and results in the precipitation of an embrittlement intermetallic phase that occurs mostly rarely at approximately 885. Additional time is required to reach maximum embrittlement at temperatures above or below 885. For example, many thousands of hours may be required to cause embrittlement at 600 F. Since 885 embrittlement can occur in relatively short periods of time, it is often assumed that susceptible materials have been exposed to temperatures in the 700 to 1000 F range are affected. The effect of toughness is not pronounced at the operating temperature, but significantly at lower temperatures experienced during plant shutdown, startups, or upsets. Embrittlement can result from tempering at higher temperatures or by holding within or cooling through the transformation range. Affected units and equipment. 885 embrittlement can be found in any unit where susceptible alloys are exposed to the embrittlement temperature range. Most refining companies limit the use of ferritic stainless steel to non-pressure boundary applications because of this damage mechanism. Common examples include fractionator trays and internal and high temperature vessels used in FCC, crude, vacuum, and coker units. Typical failures include cracking when attempting to weld or to straighten bent, upset tower trays of type 409 and 410 materials. Occur often in the vacuum tower trays of this material. Other examples include ducts, duplex, stainless steels, heat exchanger tubes, or other components exposed to temperatures above 600 F for extended periods of time. Morphology or appearance. 885 embrittlement is a metallurgical change that is not readily apparent with metallography, but can be confirmed through bent or impact testing. The existence of 885 embrittlement can be identified by an increase in hardness in affected areas. Failure during bending or impact testing of samples removed from surface is the most positive indicator of 885 embrittlement. Prevention and mitigation. The best way to prevent 885 embrittlement is to use low ferrite or non-ferrite alloys, or to avoid exposures to susceptible material to the embrittlement range. It is possible to minimize the effects of embrittlement through modifications in the chemical composition of the alloys. However, resistant materials may not always be readily available in the most commercial forms. 885 embrittlement is reversible by heat treatment to dissolve precipitants, followed by a rapid cooling. The de-embrittlement heat treatment temperature is typically 1100 F or higher, and may not be practical for many equipment items. If the de-embrittlement components is exposed to the same surface conditions, it will re-embrittle faster than it did initially. Inspection and monitoring. Impact or bending test of samples removed from surface is the most positive indicator of a problem. Most cases of embrittlement are found in the form of cracking during turnarounds or during startup or shutdown, when the material is below 200 F and the effects of embrittlement are most detrimental. An increase in hardness is another method of valuing 885 embrittlement. Snow-related mechanisms. Sample of cracked material with crazed cracks running through the grain suggesting severe embrittlement.